Twitter handles over 1 billion users, generating 58,000 write queries per second against 300,000 reads. To maintain user experience, the system must acknowledge a published tweet in under 30 milliseconds and render a timeline in under 200 milliseconds. Pushing this volume through a monolithic relational database locks up the system. Heavy SQL joins and table locking simply cannot handle this massive concurrent load. Designing an architecture capable of absorbing 300,000 requests every second requires a specialized approach to memory and processing cores. Achieving this performance necessitates breaking apart the read and write paths entirely. This system topology diagram maps that separation. There is a strict physical boundary dividing the client-facing synchronous operations on the left from the heavy asynchronous background pipelines on the right. To understand how this decoupling works in practice, we have to trace the journey of a single 1.2 kilobyte JSON tweet miniload. A mobile user hits post, initiating the data's transmission across a polyglot persistent stack. System reliability at this volume is maintained through microsecond handoffs across specialized microservices, avoiding the single point of failure inherent in a master database model. Looking at the ingress diagram, the user's tweet arrives at the network edge as a standard JSON HTTP post request, hitting the Envoy API Edge Gateway. Parsing text-based JSON payloads is computationally expensive. At 58,000 operations per second, this creates a severe processing bottleneck. To bypass this, Envoy utilizes a transcoder. It instantly translates the incoming JSON text into a compact binary gRPC protobuf message. From this edge point forward, all internal microservices communicate exclusively via these binary messages. Native's mobile apps skip this translation entirely, utilizing gRPC client stubs directly over multiplexed HTTP2 connections. The binary payload now arrives at the tweet ingestion service, ready for storage. This edge transcoding strategy supports universal web clients while maintaining binary efficiency internally. The Tweet Ingestion API validates the payload and generates a unique 64-bit K-sortable snowflake ID, embedding a precise timestamp into the data. This Phase 1 diagram shows the synchronous write. The payload is committed to the ScyllaDB master database using a fast local quorum. Writing synchronously to both the database and the Kafka event broker creates a dual write problem. If the process fails midway, the database and the event stream lose synchronization. To prevent this, the API returns a success message to the user in under 30 milliseconds before the tweet is ever distributed to followers. Background distribution is handled by Change Data Capture, or CDC. The CDC agent passively tails the database commit log. As soon as a write is confirmed, it streams the event into Apache Kafka with guaranteed at least once delivery. Decoupling ingestion from distribution prevents user-facing latency spikes while ensuring data flows reliably across the backend. This diagram tracks the event exiting Kafka and entering the fan-out worker pool. This is where the system manages write amplification. Standard distribution uses a push model. A worker writes the new tweet into the individual feed cache of every single follower. This works for regular users, but fails for celebrities. Tweeting to 100 million followers instantly triggers 100 million simultaneous database writes. These write spikes can exhaust system resources. To mitigate this, the workers rely on a hybrid router. If the author has fewer than 50,000 followers, the worker executes fast, pipelined writes into the followers' pre-computed Redis timelines. But if the author reaches the 50,000 follower threshold, the worker stops the push process. Instead, it uses a pull model. The worker writes the tweet only to the celebrity's personal feed and fires a lightweight alert signal. This routing algorithm prevents resource exhaustion during high-traffic global events. This workflow details the read path. When a follower opens their app, the timeline service must generate their feed in under 200 milliseconds. To meet this target, 99.5% of timeline read traffic bypasses the primary database and is served entirely from RAM via Redis. The engine retrieves the user's pre-computed push feed, which was populated earlier by the fan-out workers. Concurrently, the engine queries the social graph and pulls any new tweets from the independent feeds of followed celebrities. The system must now combine these disparate data streams into a single sequence. The engine feeds these streams into a min heap. By comparing the top elements of each sorted list, it rapidly sequences the final feed, avoiding the multi-second latency of a traditional database join. This hybrid read path manages celebrity write amplification while serving customized feeds in under 5 milliseconds. The final challenge is handling infinite scrolling against a dataset that is changing hundreds of thousands of times every second. Traditional SQL offset commands fail in a live feed. New incoming data shifts the results, causing the client to render duplicate or skipped posts. To solve this, the system uses seek cursor pagination, utilizing the time-encoded snowflake IDs generated during Phase 1. By passing the lowest visible snowflake ID as a hard upper bound, the system fetches strictly older tweets without offset errors. This topology shows the real-time delivery mechanism. The system prompts the user when new tweets are available without requiring the mobile app to pull the server. A server sent events maintains a low-overhead, unidirectional connection, instantly pushing a lightweight UI update to the client. Production-grade scale is achieved through pipeline decoupling, polyglot persistence, and algorithmic routing to manage the requirements of high-throughput read and write paths.